Good morning, all of you. Am I audible? Am I audible to you? Please reply me. Am I audible or not? Anyone, please respond. Anisa Chauhan.
Yes, sir.
Am I audible to you?
Yes, sir.
Okay. Thank you. So today we would be start the topic of integrator and differentiator. In the last lecture, we have learned about the topic adder as well as the subtractor. So today we would be continue with the new topic, that is ideal integrator first, and then we have to learn uh, practical integrator. There are some drawback of ideal integrator we would be learn during the analysis of this circuit. So if you have to be see, please all of you draw this diagram. This is the basic diagram of the ideal integrator circuit using op amp. If you have to be refer this diagram of the ideal integrator, this would be nothing but a simply inverting amplifier. Only the feedback resistor RF has been be replaced by a capacitor, and when you would do like this, the circuit would be converted from inverting amplifier to integrator circuit. Okay. So a circuit in which output voltage waveform is the integral of the input voltage waveform is called integrator. So if you have to be refer this integrator circuit, this is the ideal integrator circuit. Here feedback element is capacitor. You can use the term CF also or C simply. And the current drawn, we have to be know that for the case of op amp, as per this circuitry, the input voltage source is connected to the inverting terminal V in, from which a current is drawn I1, and this current would be reached to the node V2. Then it would be divided into two parts. One is IB, another is the IF. So IB would be 0 because we know that the gain of amplifier is op amp is very high. So and the input impedance is very high. Because of that, no current would be entered to the op amp. So this current is 0. Only the whole current of I1 would be diverted through the feedback network, and it would be become equal to IF. Another concept is important here, as the non-inverting terminal is connected to the ground potential. Because of that, the voltage at the terminal V1 is 0. So as per the virtual short circuit concept, V2 would be also 0, or V2 is virtually grounded, you can say. V1 is physically grounded, but V2 is virtually grounded. Okay. Now, so as per this discussion, I1 is equal to IF and V2 is equal to V1 is equal to 0 volt. When you have to be going to analyze this circuitry, that is the position condition, I1 is equal to IF. So I1 is what? V in minus 0 upon R1 according to Ohm's law. Then IF is what? Because there is a IF is passing through the feedback capacitor, so it would be in terms of capacitance we have to be derive the voltage equation, current equation. So it is, we know that for the capacitor it would be dV upon dt. So that formula we would be use here, C D V2 minus V0 upon dt, and V2 is 0 here, so it is 0 minus V0 upon dt. If you found any difficulty, you can refer the circuitry as well. So it is simply I1 V in minus V2 means 0 upon R1. Then IF is C V2 minus V0 upon dt. Okay, and V2 is here 0. So that's why it is written like this. Now we have to be integrate both sides with respect to the time from, and the limit of the integration is 0 to t. So we would be found that the equation would be now written as like this: integration of v in upon r1 dt from 0 to t is equal to integration of c dv minus dv naught upon dt into dt 0 to t. Okay, so when you have to be perform the integration, you would be found the equation would be now, I have not disturbed the LHS side, but we have to be perform integration on the RHS side. You would be found c is a constant, so it would be out of the integration. Then minus v naught, as dt would be cancelled out, so minus v naught up to this would be considered as, so it would be c minus v naught plus v naught at t is equal to 0. So this is the constant term, you can say, that is only valid for the t is equal to 0 time period. Okay, so it would be further, you can write as, what is the value of v naught at 0 time interval t is equal to 0? It is basically 0, because when t is equal to 0, output voltage would be considered as 0 volt, because there is no capacitor would be act as an open circuit at the initial condition. So there no current would be passed through the feedback network. Output voltage would be considered as 0. So in this case, what happens if you have to be considered v naught is equal to 0 at t is equal to 0 time period? Then you can write c v naught is equal to minus r1 is constant, so you can take it out from the integration sign, minus 1 upon r1. Then it is integration of v in dt from 0 to t time period. Okay, so finally you can write the equation of output voltage here. So what is the value of the output voltage? It would be v naught is equal to minus 1 upon r1 c integration of 0 to t v in dt, and this is the definition of the integrator. It would be integrate the input voltage during the period of the time, that is 0 to t here. So you can further write it as v naught is equal to minus 1 upon rc 0 to t v in dt, and rc is what? It is basically a time constant. So the output voltage is here now, it is directly proportional to the negative integral of the input voltage and inversely proportional to the time constant rc. So this is the important formula here. This is the output voltage equation for the ideal integrator. So note down all these equations that I have taught you. So still not, please take the screenshot of this. Then this one. Now if you have to be see that our output voltage is integration of the input voltage, so you can say that if the input is a sine wave, the output will be a cosine wave, because the integration of sine is cosine. If the input is a square wave, so output would be a triangular wave. So this is the effect of the integration. And for accurate integration, the time period of input signal t must be larger than or equal to RC. Okay, so this is very essential condition, that your time period of input signal must be larger than the product of resistance and capacitance RC. Okay, now this is about the ideal integrator, and this is the response that I have told you, that if you have to integrate the sine wave, it would become cosine. If you have to perform the integration for the square wave, it would become triangular. Okay, and the corresponding equations are also written here. you can note it down or take the screenshot of this simply. You can see here, it is very simple. This is the cosine that is start from the 0, then pi by 2, then pi, then 3 pi by 2, then 2 pi. And it would be start directly from the, you can say the phase difference between these two is the 90 degree. That's why it is called a cosine. Okay. So this is your sine wave and it is your cosine wave. It is the effect of integration only. Okay. Now, but it is in the negative side. That's why it is shown as the below of this time axis. That you have to be remembered. Now, we can also represent the frequency response of ideal indicator in the terms of gain versus relationship between the gain and frequency. So this is the same circuit that we have seen in the first slide. So you can define the gain as it is similar to the inverting amplifier. So as per the formula of gain of the inverting, minus Rf upon R. Here Rf is replaced by the capacitor. Okay, so it would be minus the capacitor. There is a reactance offered by the capacitor is minus J Xc upon R. And what is the Xc? Xc is basically 1 upon omega c or 1 upon 2 pi f c. So you can write it 1 upon J, negative sign would be replaced when J would be goes into the denominator, 2 pi f c into R. Okay. So what is the magnitude of this gain formula? We have to be take this magnitude, and when you have to be take the magnitude of this gain, you would be found that from the frequency response. Here you can see in the y-axis the gain and x-axis is the frequency is there. Your gain would be, as the frequency increases, at the minimum frequency or zero frequency, the gain is maximum. But as the frequency increases, gain start to decreasing, and it will be start to decreasing linearly at the rate of minus 20 dB per decade, because the x-axis is in the decibel scale actually, y-axis is a decibel scale, and x-axis is in the log scale is there. So it would be plotted in like this way, minus 20 dB per decade. Okay, and it would be decayed till the frequency of FB. FB is the frequency limiting frequency, you can say, of break frequency, because at that frequency what happens, you can say it is a gain of the amplifier will be decreased up to the 1. So it is a unity gain frequency. FB is what? Unity gain frequency. The gain of the op amp at this frequency would be 1, that is 0 dB. Okay. So you can take the amplitude of this, and we know that at FB, when FB is replaced by FB, gain is would be equal to 1. So FB would be what? It is would be equal to 1 upon 2 pi RC. This is a very important formula for unity gain frequency. And if you have to substitute the value of FB on this equation of the gain here, so you would be found that mod of A or magnitude of gain is 1 upon F upon FB. FB is what? 1 upon 2 pi RC. Okay. So you can represent here the gain of the amplifier with respect to the frequency. So as the frequency increases, your gain would be decreases. As per this relationship also it is clear. And when it would be reached to the 1, FB, the FB upon 1, the gain would be become 1 or 0 dB. Okay. So this is a frequency response of ideal indicator. But you have to be see, this ideal indicator have some drawbacks. What drawbacks? You can see from this frequency response also. The bandwidth of ideal indicator is very small, and it is used for only small ranges of input frequencies. At low frequency, op amp goes into the saturation, because at the low frequency, open loop gain is very high, nearly infinite. That's why it would be goes in saturation level at the very low frequency. That is also one of the drawbacks. And due to such all limitations, ideal indicator needs to be modified. And this modified version of the ideal indicator is called as a practical indicator. So now we have to refer the circuit of the practical indicator. So what changes we have done, or what modification we have to be do to avoid the drawbacks of the ideal indicator? You can see it is a very simple modification is done. We have add a feedback resistor parallel to the feedback capacitor, that is RF. Okay. So what is the benefit of this? When you have to be connect RF in this way, it would be avoid the op-amp going into the open loop configuration at low frequency, because at time t is equal to 0 or very low frequency, your capacitor is open and open loop gain is very high. Okay, so when you have to be use the RF, so at the low frequency, reactance offered by the capacitance would be even low. It would be even act as open circuit, but RF would be maintain the stability of the circuit. Okay, or it would be maintain the gain of the amplifier to that stable level or finite level. It would does not. It would be actually stop the op-amp to goes into the infinite gain. Okay. So now we have to do the analysis and see the operation of this practical indicator. I hope all of you have drawn this or take the screenshot of this diagram. Now we have to be moved to the analysis of this circuitry. Okay. So when you have to be moved for the analysis of this circuitry, this is the final diagram of the practical indicator. Now we have to find out the expression for output voltage. So please copy this diagram. So here you can see that diagram also you can refer from the Ramakant Gaikwad book of the op-amp. That is also given the same diagram. So here you can directly connect the non-inverting terminal to the ground as well, or you can connect a R ohm or R comp resistor that is equivalent to the R1. Okay, it is very small resistor actually. Then inverting terminal as usual, it is the R1 is there, and only modification we have done, we have added the RF in parallel to the CF. Okay, and is the load resistor RL is there. Now you can see this practical indicator circuit here. Feedback capacitor is shunted by the RF, so the gain of the indicator is at low frequency is limited by any saturation problem. Now you have to analysis. I1 is flowing through the R1. When it would reach to this node at V2, it would be divided in two parts, IV and IF. But as IF is 0 because of very high open loop gain and high input impedance of the op-amp, so whole I1 would be diverted to the IF through the feedback network. So now we have to be see that since the parallel capacitor combination of RF and capacitor CF dissipate the power, that's why this practical indicator is also referred as a lossy indicator. The name, another name of this circuitry is lossy indicator. Because of that, the power dissipate with the addition of RF parallel to the CF. The resistor RF provide, first of all, DC stabilization. This is the main advantage of this, by limiting the low frequency gain to minus RF upon R1. What happens at the low frequency? We know that the capacitor having the property at a low frequency or nearly zero frequency, what happens? It would be become infinite. And if the reactance is infinite, no current would be allowed to flow through the capacitor. It would be act as a open circuit. So at that time, your circuit would be become open loop circuit and gain would be become infinite, because open loop gain of the op-amp is nearly infinite. So avoid this problem of saturation at low frequency. What happens? RF is connected in parallel to that, and because of that, your gain would be limited to minus RF upon R1 at low frequencies. Okay, and the resistor R comp or R ohm is given by R1 parallel RF, as RF is very large value compared to the R1. So what happens? R comp would be nearly equivalent to the R1. That is very small value. You can omit this from the circuitry also. That is also correct. Okay. Now, what is the value of voltage gain of the indicator? So we would be represent this in terms of Laplace transform. So in this Laplace transform, you can see the gain is V naught upon V in, and S domain it has been shown here is equal to minus, here instead of RS we have to use the impedance ZF, because there is a combination of capacitor and resistor, and instead of R1 we have to use the Z1, because we are doing the Laplace transform, so we have to be consider the terms impedance instead of resistance only. So what is the value of ZF? It is a parallel combination of RF and CF. So it would be become RF parallel 1 upon SCF or omega CF, you can say. S means J omega. You have all are aware of this term for the Laplace transform. So you have to do this. You would be find final relationship RF upon RF CF S plus 1 for this parallel combination. In the another side, Z1 is what? R1 only. There is no another capacitor or other components. It is simply R1. So substitute the value of ZF and Z1S into this equation of voltage gain. You would be found this value would be as, for the safe side or for easiness you can give the equation numbers. This will be also helpful for you. So substitute the value of equation number 2 and 3 into the equation number 1. You would be got V naught upon V in is equal to minus RF upon R1 RF CF S plus 1. So here RF plus R1 upon R1 is gain constant. Okay. And the break frequency means the frequency at which the practical indicator gain would be decreased to the 70% of the maximum gain, or that is called the cutoff frequency. Actually, your gain would be decreased by the 1 upon root 2 or 0.707 of the actual gain or maximum gain, can be calculated when this would be denominator has to be substituted or equivalent to the root 2, because at this frequency your gain would be decreased by the 1 upon root 2. So you can say that denominator is equivalent to the root 2. So when you do this, so only you have to take the amplitude part. So it will be amplitude of this equation is, so denominator section square root of 1 plus RF CF S. Instead of that you have to be use the 2 pi f square is equivalent to the root 2. That would be give you at the frequency f is equal to fa, that is called the breaking frequency. Actually you would be get fa is equal to 1 upon 2 pi f RF. This is very important relationship. Okay, so how this would be came, it would be take the square, so it would be become RF CF 2 pi f A in up equal to 2. So RF CF 2 pi f A is equal to 2 minus 1 1. So f A is equal to 1 upon 2 pi RF. Okay, so this is very simple derivation. So at this breaking frequency, what happens? Your gain would be decreased by the amount of 3 dB or 70% of the maximum gain. Okay. So generally, the value of FA in terms R1 CF or RF CF value should be selected such that your this breaking frequency should be always less than unity gain frequency. FA should be always less than the FB. FB is what? Unity gain frequency, that we have already seen in the ideal integrator, and FA is the breaking frequency or limiting frequency. So if you have to be seen, typically FA is 1 upon 10 times of the FB. So breaking frequency is always less than by the 10 times of the unity gain frequency. So if you have to be considered this relationship, then you can also correlate that RA would be 10 times greater than the R1. This is a very standard relationship. You can follow this for the numerical solving also. So for the proper integration of the input signal having a time period T, should be the following conditions should be satisfied. That is, T should be less than or equal to product of RF CF. Okay. So you can see this through the frequency response also. Here you can easily see that this is the basic or ideal indicator frequency response, that is decreases linearly when you increase the frequency by the amount of minus 20 dB per decade. But we have to be see this dark line, that is the practical indicator. The gain is constant till it would be not reached to the FA. At the FA, that a limiting frequency, your gain would be decreased by the this 3 dB. This is the 3 dB decrement. And FA is always less than the FB. FB is unity gain frequency, and means in the decibel scale 0 dB. So your in this particular region, your circuit would be act as a indicator. Okay. In this region, it is a constant gain, so it is not acting as the indicator. But in this way, where the gain is decreases, you can say the actual response of the practical indicator when the frequency is in between FA and FB. Okay. You can also derive the frequency response mathematically in the terms of gain and frequency relationship. That also we would be just referred to here in the next slide. And please draw this diagram. This is or take the screenshot. It is very important relationship. Okay, just take this screenshot. Okay, now we have to move to the next section of this gain versus frequency relationship in the frequency response of practical indicator. Simply you can write the gain, that is parallel combination of this upon R. I have not taken the negative sign. You can take also. There is not any issue because it is inverting combination. So you have to do this parallel combination. Finally, you would be got A is equal to minus RF upon R 1 upon 1 plus J 2 pi F RF C. Okay. So this is the relationship between the gain versus frequency. Now you can see what is the breaking frequency FA. FA is equal to 1 upon 2 pi FC RF C. So you can say it as A is equal to minus RF upon R 1 upon 1 plus J F divided by FA, because FA is 1 upon 2 pi RF C, that we have already seen. So here F is the operating frequency and FA is the breaking frequency or corner frequency, where your gain is decreased by the 3 dB. Okay. Now this is the relationship between the operating frequency and the voltage gain offered by this practical indicator circuit. When you have to represent this in the graphical way, so there is a graph between the gain versus frequency is there. You can see here, this is a very simply we have drawn and shown the corner frequency or unity gain frequency as well. So there are some conditions from this formula. This formula is very important. Please note it down. And here we have omit the negative sign because we have taken only amplitude. So when F is equal to 0, when F is equal to 0, your gain is equivalent to mod of RF upon R. This is called the DC gain. But when your operating frequency is in between 0 and breaking frequency, so your gain would be nearly equal to RF upon R, or maybe little bit greater than this, but it is nearly equal to. But when F is greater than FA, means breaking frequency more than this, your gain would be start to decrease, and it is less than the value of RF upon R. And when it would be reached to the FB, it would be 1. And when operating frequency is equal to corner frequency, your gain would be RF upon R 1 upon root 2. That is 0.707 times of RF upon R, 71% of the actual maximum gain. So true integration is possible when the frequency, operating frequency in between FA and FB. This is the reason. And for better integration, your FB should be greater than or equal to 10 times the FA. Okay. So these are the some standard relationship that you have to be follow when you have to be designing any integrator circuitry. Okay. So please take this screenshot. This is very important facts that I have shown in the slide. That would be also useful for the objective questions as well. Okay. Now we have to be moved to the one of the question I have taken. Design a practical indicator using op-amp IC741C to satisfy the following specification. Assume VCC is equal to plus minus 15 volts, and then 3 dB cutoff frequency is 1.5 kilohertz. That means FA is given, and DC gain RF upon R is 10 is given. So sketch the frequency response of this. Okay. So for this, I hope all of you have taken noted down this question. So it is we have to be just draw the frequency response, gain versus frequency curve. But for that little bit the values of the frequency and gain we have to be know, so that we have to correctly plot the graph. So for this you can see the answer. This is the graph that actually required to draw. So FA is what? 1/2 pi RFC. We have to assume the value of C is 0.1 microfarad. So you would be get the value of RF, that is 1.061 kilo ohm, nearly 1 kilo ohm. And for the good indication, we know that unity gain frequency is 10 times the corner frequency. So it would become 15 kilohertz. At 15 kilohertz, the gain would be decreased to the 1. So at that time, you can find out the R again. Okay. So it is 106.1 ohm. And R ohm is, this is the resistor that is used in the non-inverting terminal. R plus RF, that is 96 ohm. That is very small value. You can neglect also. So DC gain is 10. So in decibel, the value of DC gain is 20 dB. You can see here, this gain has been shown here. It is stable up to this point, but when you would be increase the frequency up to FA, it would be decreased by the minus 3 dB. And after that, it would be act as a perfect indicator, and your gain would be linearly decreased by the minus 20 dB per decade. Okay. So this is the way you have to be solved. Actually, in this topic, you have to be solved lots of the design numericals based on the indicators. So please refer your whatever the book you are referring and solve the numericals. The numericals would be expected from this topic. If the time permits, we will also take the numericals in the next lecture as well. Okay. Now we have to move to the next circuitry, that is differentiator. So the name it suggests that what is the function of this circuitry. This operation amplifier circuit performs the mathematical operation of differentiation. That is, it produces a voltage output which is directly proportional to the input voltage rate of change with respect to time. Means V0 is a function of dV in upon dt. Okay. So in other words, you can say the faster or larger the change into the input voltage signal, the greater the input current, and greater will be the output voltage change as in response, and become more spikes in the shape. If there is a square waveform as input, you would be get more and more spikes as a output waveform because of the differentiation operation. Okay. So after the definition, we have to see the differentiator circuit. Again, we have to start with the ideal differentiator, and then we have to move to the practical differentiator. So this is a very simple diagram of the ideal differentiator. This is also one kind of inverting amplifier. What we have only do, instead of R1, we have to be replace it by the capacitor. Here the feedback resistance is same as in the inverting amplifier, only the R1 is replaced by the C. Okay. So the expression for the output voltage can be obtained from the Kirchhoff's current equation on this particular node that you can see, that is V0, V2. So as non-inverting terminal is connected to the ground, so as per the virtual ground constant, V2 is also equal to 0. And in this node, the KCL apply, I1 is equal to IB plus IF. IB is 0, we know that, the reason behind it. So I1 is equivalent to the IF. So what is I in? As the capacitor is involved here, it is C D V in minus V2 upon dt. And what is the another part of this current, that is IF? This is V02 minus V0 upon RF. Okay. So this is a simple way of deriving the current equations. And from this derivation, we have to be come to the relationship of the output voltage and input voltage. But we know that according to virtual short circuit concept, V1 is equal to V2, so it would be equal to 0 volt. So C d V in minus 0 upon dt is equal to 0 minus V0 upon Rf. Okay. So noted down all the equations simultaneously. That would be helpful for you with your equation number. Okay. So now what is the final equation is there? This would be C dV in upon dt is equal to minus V0 upon Rf, or you can finally write the equation of output voltage. Okay, that is V0 is equal to minus Rfc dV in upon dt. So in this way, you can see that the output voltage V0 is equal to Rc times the negative instantaneous value of the rate of change of the input voltage V in with respect to the time. So this is the relationship between the input and output voltages. And it would be from the equation number 4, it is very much clear. Output voltage is the differentiation of the input voltage with respect to time. So a cosine wave input produces the sine wave output, because we have to take the d cos theta upon, so it would become a sine theta. So similarly, a cosine wave would be converted into sine wave would be converted into the cosine wave, and also some other square wave is converted in some spikes. You can see here through the diagram. So it is very much clear. When the input voltage is a square wave, that would be converted into the some spikes is here, and for the sinusoidal sine wave, it is the cosine wave either, or vice versa. So the input signal with the differentiated properly if so time period t of the input signal is larger than or equal to Rfc. So as the frequency changes, gain also changes. Means as the frequency increases, your gain would be also susceptible to the high frequency noise as well. So at the high frequency, what happens? Your circuit would be become more susceptible to the noise, and along with the your input signal, noise would be also getting amplified. This is the one of the drawback of the ideal differentiator. Okay, please note it down this or take the screenshot of this diagram. So what is the solution for this? This is the problem of the adding the or amplifying the noise in the at the high frequency. The solution is we have to use a practical differentiator. So we have to do certain modification on the ideal integrator circuit. So see what modification we have done. Please note it on this diagram as well simultaneously. Here we have add a parallel capacitor CF in the feedback network along with the RF, and also connect our resistor R1 in series with the input capacitance C1. And rest of the circuit is similarly same. You can connect this or not, R comp or R ohm. It is nothing but your parallel combination of this RF CF parallel with respect to the R1 C1 in series. So this is also a very small value. Okay. So this is the modification that we have to be done so that your problem of the noise amplification would be sorted out in the case of differentiator circuitry. So now we have to going to analyze this differentiator circuitry. Okay. So please note it down this diagram. I will give you the 30-second time for this. Otherwise, you would not understand the analysis. This diagram is very much important. And why we have to be modification done in this ideal differentiator? To avoid the problem of the instability as well as the high frequency noise that is added during the ideal differentiator case at the high frequency signals. Okay. Now, both at the high frequency noise and instability problem can be corrected by added this components that we have shown in the diagram. Okay. So what happens in the high frequency? If you have to be see at the high frequency, what happens? The reactance offered by the CF would be very low at the high frequency, and because of that, what happens? The gain of the differentiator would be increases drastically. So at the high frequency, what happens? The reactance offered by this capacitor is very low, and because of that, the gain would be increased very drastically. To limit this increase in the gain, we have to be connect R1 in series. Okay. So this is the some way that we have to be controlled. We have to see from the analysis how this is happening. Now, the voltage gain of the differentiator, again we have to be write the gain formula in terms of Laplace transform. So it is V naught S upon V in S is equal to minus ZFS upon Z1S. Here we have to use the term of impedance because there is a combination of resistor and capacitor. So this would be ZF is what? If you have to see, ZF is a parallel combination of RF and CF. You can write it as RF parallel 1 upon SCF, that is RF upon 1 plus RF CF S. S is J omega. Similarly, in the series combination input side, R1 plus 1 upon SC1. So it would become 1 plus R1 C1 S upon C1 S. Okay. So note it down these equations. Further, we have to be what? We have to substitute the value of ZF and Z1S in the equation number 1. So the new relationship between the V0 and V in would be there, and that is V0 S upon V in S is equal to minus RF C1 S upon RF CF S plus 1 into R1 C1 S plus R1. So this is very much simple. You have to be just substitute in the numerator and denominator these two values, and you would be get this relationship. Okay. So this is your equation number 4. If here, if to be substitute RF CF is equal to R1 C1, so the transfer function would be now V0 upon V in S is equal to minus RF C1 S upon 1 plus RF CF S whole square. This is your equation number 5. So what happens? At the frequency F is equal to FB, at which the frequency response of the practical differentiator start to decreasing at 20 dB per decade, can be determined using or equating the denominator of the above term to 0. So therefore, you can also write it as RF CF S plus 1 whole square is equal to 0. Here you would be get a value of in this way. Just write this, then we have to see. However, in this equation, S is what? It is J omega, means J into 2 pi F, and F at F is equal to FA, that is the limiting frequency. It can't be a negative value, and therefore FB would be what? 1 upon 2 pi R1 C1. FB is what? 1 upon 2 pi R1 C1. Okay. So in this case, we know that R1 C1 is equal to RF CF, means FB could be also written as either 1 upon RF 2 pi R1C1 or 2 pi RFCF. Both are correct because we have taken R1C1 is same. Product of R1C1 is equal to RFCF. Okay. So value of FP is selected in such a way that it should be lie between FA and FC. Okay. So FC is what? The frequency at which the gain is becomes equal to the you can say 0 in decibel scale. Okay. So this is the important relationship is here that you can see from this particular diagram of the frequency response as well. You can see here this is the gain versus frequency curve. This is the open loop gain of ideal differentiator. It is the ideal differentiator, you can say, and these two are the practical differentiator. So here this is your FA, this is the point, this is the point, you can say FB, and this is the point when it is a FC, and it would be start from -20, and then you can say it is a 0, then you can say it is at 20, then 40, then 60, like this up to the 100 dB or maybe more. You have to show here 100 dB, and here you can see it is FA, that is 10 times of F basic fundamental frequency. Then it would be increases with the term 10 square F, then it would be increasing with 10 to the power 3F, then 10 to the power 4F, like this. It would be increases. Okay. So on. So what happens? It is lots of the conjunctions. So I'm not writing this. I'm directly indicating the so much jumbled here. So it will be difficult to answer. Simply you have to understand that at FA, this is the you can say the gain of the differentiator would be nearly 0 dB or 1, you can say, and FB, the gain would be your, it would be practical differentiator would be increase at the rate of 20 dB per decade as compared to the previous. The gain practical differentiator is increases. Okay, but after FB, when the frequency is greater than FB and less than FC, it would be again start to decrease by the amount of 20 dB per decade. Okay, so this is the frequency response of the differentiator, practical and ideal differentiator on the same graph. So FB is what here? Gain limiting frequency. And the value of FB should be in between FA and FC for the proper differentiation. So this is all about the differentiator. So today we have learned the integrator as well as the differentiator in this lecture. There is a scope of numericals. Please put up the attendance on your chat box as well. So you can there is a scope of asking the numericals on both of the topic of differentiator and the integrator. if you have to see the application of indicator, it is used in the ADC, and application of differentiator would be used in the high pass filter or PID controller. Also, we have to use the differentiator, or some wave shaping circuits. We have to also use the differentiators are there. So in the next lecture, I will be take instrumentation amplifier as well as the some numericals of the indicators and differentiator. Okay, so please put up your attendance, and if anyone has any question, you can ask me regarding today's lecture or maybe yesterday's lecture. Only in this case of the question would be asked like that, design a differentiator to differentiate the input signal that varies from some frequency to some frequency. Okay, and at that time you have to be find out the value of C1, RF, CF, like this. All components value have to be find out for to achieve such condition of the frequencies. Similarly for the integrator as well. Okay, so that is also very much important. I am again repeating, go through some numericals. We would also take the numericals tomorrow. Anyone has any question, please ask me. Or fill up the attendance quickly. What is the question? Please ask me. Vaishnavi. In the last lecture, we have also learned the adder and subtractor. That is also very important topic. In the last lecture, lots of the interruption of the internet was there, but refer the topic that I would be going to share you the video also. Once again, I have recording the that video on a composite way, so that you would be available in one lecture also, and I would be upload on the YouTube. Anyone has any question? Okay, it is looking like that no one is asking, so we would be stop here today. Thank you all of you for attending the lecture. Thanks a lot.